welcome back. We are going to finish up our discussion on the correlation coefficient today. We're going to find out what it tells us and maybe what it doesn't. So, I hope you can see the values on my calculator over here. I want you to take a calculator and type those values into L1 and L2. And then I want you to calculate R. Remember, to do that, you're going to have to go to linreg in your calculator. So pause the video for a sec, put those numbers in, find out what R is. Come back when you've got it. Okay, so for R, I got 0.975. By the way, if you have your own calculator, then remember how we turned on diagnostic on to get the R and R squared here? If you've got a physical calculator, you only ever have to do that once. It should show up every time after that. If you're using the online graphing calculator for now because you don't have one of your own, every time you open the page, you're going to have to go to diagnostic on in the catalog. That's kind of a pain, but it's the price you pay for not paying a price for a calculator. So, R is 0.975. What does that mean for our data set? Does that mean there is a strong positive relationship that's linear between x and y? I didn't give you any context on those variables, I just gave you the values. But based on this value of R, this is really close to 1. Does that mean there's a strong positive linear relationship between the two variables? No, it doesn't. R is interpreted as the strength and direction of a linear relationship. But R can be calculated no matter what the relationship looks like. You may have noticed something as you were typing in those numbers. X was the numbers 1 through 10. Y was x squared. So if you were to look at the scatter plot, that's what you see. You see a clearly curved pattern in the data, and we're trying to fit a straight line to it when we do linear regression. R is close to 1. But just because you can calculate R does not mean the relationship between the variables is linear. So, before interpreting R, ensure the relationship is linear. Because if the relationship is not linear, this correlation coefficient is meaningless. It means absolutely jack squat. Nothing. Zip zilch nada. Okay? How can you ensure the relationship is linear? Well, one way is to look at a scatter plot so you can see it visually. In some questions, you may be told the relationship is linear and also be given R, in which case you can interpret that as a strong positive linear relationship. But if you're just given a problem and you're told what R is, you can't interpret this if you don't know the relationship is linear in nature. This does not tell you that it's linear. R has no clue. You just plug in the numbers. You, as a human, are the one that has to determine if the relationship is linear, either through a scatter plot or by being told so ahead of time. So that's a very important thing about using the correlation coefficient. It does not tell you anything unless you know the relationship is linear already. I know I've repeated myself like 5 times, but it really is that important because they will try to trick you. And by they, sometimes I mean me. I've been known to do that. Okay, so let's go ahead and actually talk about how R is calculated. So R is equal to, and you'll see me staring at my notes repeatedly because I actually don't have this formula committed to memory, and you don't have to either. The formula for the correlation coefficient is on the formula sheet for the AP exam, so you don't have to memorize it either. But you should know where this comes from. not done yet. There it is. This is how the correlation coefficient is calculated if you've got all your X data and all your Y data. I've never seen a problem on an AP exam that asked you to calculate the correlation coefficient by hand. First of all, if they asked you to do that with multiple choice, you could just use the calculator and do linreg and get R. And to do that on a free response question would be out of the question. I don't think they will ever do that. But it's important that you know how it's calculated. You're essentially taking each individual either X value or Y value, determining how far it is from the mean, dividing by the standard deviation, essentially the z-score for each X value and each Y value, taking the product of those, adding them all up, and dividing by n minus 1. So the number of values you have minus 1. And that's R. So this will tend to be negative if the relationship goes down and to the right. R will tend to be a positive value if you have a positive relationship that goes up and to the right. Again, you don't need to memorize this. You probably don't even need to utilize it. But it can be useful to know how it is calculated so it's not just like this mysterious thing that no one knows anything about. This is how it's calculated. All right. We talked about how R is only meaningful if the association is linear. So in a case like this, you wouldn't want to interpret R as a strong positive linear relationship because you'd be a doofus to do that. This is not linear, obviously. So either analyze the scatter plot before you interpret what R stands for, or be told ahead of time, essentially. Cool. All right, so I've got more examples. Let me put the next one on the board. We'll get rid of this calculator, and I will cut straight to that. All right, here's my next question for you. Suppose R is calculated for a bivariate data set, 2 variables, and R is equal to negative 0.87. Does this indicate a strong negative linear association between the variables? R equals negative 0.87. That's pretty close to negative 1, right? So that's pretty strong. And it's negative, so it's negative. And R measures linear relationships, right? So is that what this indicates? Nope. No. I'll point you right there. Okay? Unless you know the relationship is linear, this doesn't tell you much. Chances are, if R is negative 0.87, the relationship is strong and it is negative. But you can't assume that that is a linear relationship. You have to ensure that some other way, whether it's from the scatter plot or being told so. Okay? If it feels like I'm just repeating the same thing over and over, good, I am, yes. This is an important concept. This is a very common mistake among students. They see that R is calculated, they know what it represents, and they just apply it whenever they see it. Be a little more critical in how you interpret this value. It is very important that you don't misapply how this is used. All right. Let's see, what do I want to talk about next? Okay. Another example. Give me just one moment. Okay, let's take a look at what's in blue here. So, suppose you're analyzing the relationship between exercise and skin cancer. You gather data, somehow you gather data on these 2 variables, and a scatter plot reveals a linear relationship with R equals 0.75. Fairly strong positive relationship. So this suggests those who exercise more tend to be more likely to develop skin cancer. This is based on an actual study. I got it out of a different stats textbook than the one that we use, and they cited their source is a medical study. So that is true. Is this what we can conclude from our findings? Scatter plot reveals a linear relationship. So we can interpret R being 0.75 as indicating a strong positive linear relationship. All that's saying is that the scatter plot does this, which means as exercise increases, skin cancer propensity also increases. That's what this is saying. And that's interesting. But that's the question we really want to know. Does exercise cause skin cancer? That's an interesting question. That would be kind of scary if it did, right? Is that how we can interpret this number? We're saying there's a strong positive linear relationship. They tend to be linked. They tend to move in the same direction. So can we conclude that exercise causes skin cancer? More exercise, more skin cancer. Well, okay, let's think about this just using common sense. We're not using statistics right now. Let's suppose this was true. And let's say for the next 365 days, I resolve to do 100 sit-ups and 100 push-ups in my office every day. That would be constituted as exercise. And considering my current shape, that would take me a very long time to do. So it's a lot of exercise. Would that make me at higher risk of skin cancer? Well, that might require you to know something about skin cancer. What really is the catalyst for this? You're going to have a hard time convincing me that exercise is the cause of skin cancer, but what really is the cause? The sun. High exposure to the sun causes a higher likelihood of skin cancer. This is why you wear sunscreen and sunblock when you go outside, especially when you go out to like the beach where you're going to be out there for a while. Because otherwise, the UV rays are kind of harmful. They can give you skin cancer. So it's not exercise. It's the sun. So then why are we seeing this? Probably because most forms of exercise are done outdoors. Running, sports, hiking, like most exercise is outdoors. And chances are, if you're outside, it's going to be a fairly nice day. So, sun's out. People who do that over and over and over have a higher likelihood of getting skin cancer. So, we're seeing this, which would suggest this. But we're pretty confident that the cause is actually something else. How could we prove that? So how can we prove? How could we prove sun exposure, not exercise, is a primary cause of skin cancer? Right? Because just interpreting this value, it would appear as though this is true, but we are pretty confident it's actually something else. So how is it that humans know this isn't true, despite what the data might say? How could we prove otherwise? Well, we could perform an experiment. And there will be, if not an entire unit, at least a good chunk of a unit devoted to how to conduct a legitimate randomized experiment to determine whether something affects something else. But we can at least briefly discuss how we could design this experiment in order to determine if this is the case or not. So give me just a second. My cat is really annoying me and she wants to leave this room. So, okay, the cat is gone. Yay. So, how could we perform an experiment here? Let's say we take 1,000 volunteers. And we want to determine whether exercise is the cause of skin cancer or whether it's exposure to the sun. So wouldn't it make sense to split these people into groups where we vary the amount of exercise they do and the amount of sun exposure they get? So I'm thinking 4 groups. So 250 people each. So there are going to be 4 different treatments here. The first group, we'll have them exercise outside. We'll say 1 hour a day. And exercise can be anything. It could be just a brisk walk, a run if you're able to run that long, sit-ups or push-ups as long as they're outside, whatever you consider exercise. Playing a sport. Another 250 people are going to exercise inside. So, depending on the level of control we want to have, we could ask these people to do the exact same exercise regimen. And that might be a good idea. So maybe you walk around for half an hour and then you go play at a local basketball court for half an hour. Whatever, something. Doesn't really matter. Okay? But just the difference between these 2 groups should tell us whether it should tell us whether being outside or inside affects your rate of skin cancer, right? Because if a lot more people in this group get it than in this group, that tells us really the only variable involved was whether they were outside or inside. So why don't we just have those 2 groups? Well, because everyone here is exercising. If we want to know the answer to this question, we have to have people that aren't exercising. So we have 250 people in 2 other groups. We'll have them spend some time outside but not exercising. Maybe they're just soaking up rays in the sun, right? That would be ideal. Okay. And again, that could be an hour a day. And obviously we can't control everything in these people's lives. Maybe they would be outside for more than just that 1 hour just because they have to go somewhere, do something. But we would have them set aside an hour every day to be outside other than what they would normally do. And the last 250 people would be no exercise inside. And again, that would be for an hour a day. Okay. So we're not saying that they're only inside for that hour or only outside for that hour, but that they are setting that time aside to either be outside or inside, exercising or not. So we could gather data from all of these people and we could measure how much exercise they did, how many calories they burned. You could get that from a Fitbit or something like that. And you could, I'm not sure how they measure this, but you could measure I don't even want to hazard a guess, but there is a way for people to measure something about whether you have skin cancer or whether you're at risk for it or whatever. Okay. So if we see differences between these groups, we could, since we did an experiment here, we could attribute those differences to either the exercise or to where they did their exercise, right? So that would be the only way to settle this, is to do an experiment, right? Just because this correlation is high does not mean that exercise causes skin cancer. And this actually brings up a phrase that is fairly commonly known, even among just the general public, and that is correlation does not imply causation. Just because two things have a high correlation does not mean that one causes the other. In order for something to imply a cause of something else, in order for something to influence something else and to be able to conclude that, you must perform an experiment. If you're just doing an observational study, just gathering data, and you see a correlation, that's all you can say. Hey, isn't it nice that these two variables tend to increase together? Or that as one variable increases, the other one decreases. That's all you can say. You're not allowed to be the expert in skin cancer or exercise. You're just a statistician. Statistician is a number cruncher. And if the numbers say that the correlation is 0.75, that's great. You can say there's a strong, positive, linear relationship. But you cannot say this unless you do an experiment. And we will revisit this idea later, but I thought I'd include it here because it's centrally involved with correlation. So, I want to make a big deal about that. Is that all I wanted to say? Okay, so again, the reason why an experiment allows you to say something like this, or to disprove it, is because you are accounting for all those other variables. So for example, in this experiment, we are accounting for sun exposure. If we were to see a difference in the propensity of skin cancer between these two groups and these two groups, then maybe this is true. But we will know that because we already accounted for whether they're being exposed to the sun or not. Okay? Without doing an experiment, anything could be causing skin cancer. We would have no idea. The experiment has to be done to allow for the effects of other variables. Good. So, there's actually one more thing that I want to talk about that's related to this statement, and I think you'll find it pretty interesting. So give me just 1 second. So this is a really cool website. I know I've shown you a lot of these lately. There's a lot of fun statistics on the internet, believe it or not. This is Spurious Correlations by this guy, Tyler Vigen, or Vegan? I don't know how it's pronounced. And apparently he's got a book about this stuff. But this whole website is devoted to discovering relationships between variables that have nothing to do with each other. So, for example, the United States spending on science, space, and technology correlates with suicides by hanging, strangulation, and suffocation. The correlation is 0.9979. And you can see here in this time series plot how closely related those two variables are. But could you honestly say that one of these causes changes in the other? That would be ridiculous, right? Even though they're so highly correlated. And this is from 1999 to 2009. This website is old. It'd be interesting to see in the past 10 years or so if that correlation has continued. But this entire website is devoted to, where is it? This concept right here. Right? So a lot of these have a morbid fascination. They have to do with like people dying. I don't know why. So the number of people who drown by falling into a pool correlates with films Nicolas Cage appeared in. They very much increased in 2007, but then dipped in 2008 and came back in 2009. What? Per capita cheese consumption correlates with the number of people who die by becoming tangled in their bed sheets. Wow. How about this? Is measured in the hundreds. Holy cow. Yeah, correlation 0.9471. The divorce rate in Maine correlates with the per capita consumption of margarine. Cool. We've got a little dairy theme going on here. This one doesn't have anything to do with death, though, so that's good. So I hope that in this video you've learned two things, mainly about what correlation doesn't say. Correlation does not tell you a relationship is linear, right? You can calculate correlation for any bivariate data set. You have to verify through a scatter plot or through the prompt of the question whether the relationship is linear and how you can interpret the correlation coefficient R. Also, correlation doesn't imply causation. Just because R is insanely high doesn't necessarily mean one variable causes change in the other. You might think it does. That doesn't make it true. If I told you that there was a high correlation between number of hours studied and GPA for students, you might say, well, yeah, duh, studying for longer makes your GPA go higher. You can't say that without doing an experiment. It might make sense. You might be able to see the link, but as a statistician, you got to keep your hands off saying X causes Y. You can't, because there might actually be other stuff going on there that you're not taking into account. That's the thing about being a statistician. You gotta kind of be humble and always be like cynical and thinking that there's something out there that could be affecting the relationship. So that is enough for our correlation discussion. Now, correlation's not going away. We're going to get into linear regression starting in the next video, and correlation is part of that. But in terms of correlation as its own thing, we're going to put that off to the side and really focus on what it means to do a linear regression. What do you have to know about the data first? What does it tell you? How can we interpret the results? So I'm very excited to start that with you. So stick around for the next video. And until then, have a great day.